So when we go to solve a physics problem, we've been doing this a lot lately, but tell me what step one is.
Read.
An answer.
We're gonna read, no, I'm recording, I don't want any sarcasm or any distractions.
Draw a pic.
Part two is draw a pic, right? We're gonna draw a picture of it. So then what's step three?
Label. Label. The picture.
Label, but we do label the picture, but what's the word Mr. Adams uses?
No.
Knows. We label what we know.
Need to know.
Number four, the next step is
Need to know.
need to knows. 5,
Equation.
we have to take that information and we list the equations, right? 6, solve. And then I added a step 7. Who can tell me what?
Simplify.
No,
Check your
check your work, but how do we double check it?
In the back.
And the calculator.
In the back in the calculator. Yeah, there's a variety of ways, but really, sometimes what I like to do is I call it a common sense check.
Yes.
And so let me tell you what that means. If they ask us a question like, how much time will it take, and we do a bunch of work, and our answer, we're left with like kilograms. Well, kilograms is a time. Okay? Another common sense check might be if I'm in a car and the car's going 60 kilometers an hour, and then I get an answer, like the car's going 60 kilometers an hour and it hits another car at 30 kilometers an hour, how fast will the car be going after the collision? And if my answer is like 90 kilometers an hour, that doesn't make sense, right? If I got two cars hitting each other. So not only do we have to make sure by plugging it in the calculator, right, or looking in the back of the book. Clearly, if we look in the back of the book, we're probably wrong. But we also have to make sure our answer makes sense, okay? And so, like, problem number 39, Mr. Adams didn't orientate the displacement. And so when we got our answer, the back of the book said it was like 1,000 seconds, 1,083 seconds. But when I did my calculation, I got a negative 1,083 seconds. And then somebody said, oh, that's okay. You said that going that way was negative. Yeah, but time is not negative. So we looked at the problem and we were like, okay, well, the displacement, you can be displaced in a negative direction. What I mean by that is if you're playing football, right, you can have a 5-yard gain and you can have a 5-yard loss. It's still 5 yards, but the direction, plus or minus, you could go back, minus, or forward, which would be plus. And that's kind of what we were thinking about. And the problem that I did, the guy went back 5 because he went 5 meters in the negative direction. And so then when I plugged that in, then the time worked out properly. Minor things like that is what we want to double check at the end. So now for problem number, which one's the next one on the board? 41. So for 41. Problem number 41, I gotta find it here. Problem number 41, it says consider 2 string suspended balls, both with a mass of 0.65 kilograms, similar to figure 615. So there's a picture in your book, and I'll just draw it in a second. One ball is pulled back on a line with the other so that it has a vertical height of 10 centimeters, and then it is released. What is the speed of the ball just before hitting the stationary one? If the collision is completely inelastic, to what height do the balls swing? So the 615, the figure 615, is in chapter 6, and you gotta go back, and I'll tell you the page number in a second. But it's a pendulum type thing, you know, like Newton's cradle, right?
Yeah.
And so let me find 615. Where's it at? If you guys find the page number before I do, let me know. So there's figures 627, 626, 620, so it's 615. Okay, I see. Yeah, so it's like a pendulum. Okay. So first thing we read the picture, we read the problem, then we draw the picture. So what they're saying, it's like Newton's cradle, right? So you've got two balls, and they're hanging from a string, but they're of equal length. Okay, like that. And so that's kind of the picture. Let's go back and read the problem again, just to kind of make sure. But I'm pretty sure that you're going to take the one ball and you're going to pull it back. So this is like part A, right? And then what you're going to do is you're going to pull one ball back a little bit, which would be like part B. And then part C is when you let this ball go, it's going to hit the other ball, and then we got to predict what's going to happen, I think. So let's read the problem again just to make sure. It says, consider two strings suspended balls, both with a mass of 0.15. Yeah, and then it says the figure. So we drew it just like the figure. So technically our picture's done. Now we need to list what we know. Well, what we know is that this has a mass, and I'm just going to call this mass B, right? And that's, what was it, 0.15 grams or kilograms? Kilograms. And they're the same. So this one has a mass of the same, 0.15 kilograms. So we're labeling the picture, listing what we know, okay? Then as I read on, it says, just like the figure in 615, and if we turn to 615, we have Newton's cradle. And then it says, but with only two balls, right? So that's the same picture, but with only two. One ball is pulled back in line with the other, so it has a vertical displacement or a vertical height of 10 centimeters. So what they're saying is, this ball, we'll call it B, is pulled back such that the distance between here and here is 10 centimeters. Now, if that's 10 centimeters, and we're talking about conservation of momentum, what's the unit of measure of momentum? Kilogram meters per second. So what should we do? Yeah, this probably should be a height of 0.1 meters, right? Does that sound right? Okay. And then it's released. What is the speed of the ball just before hitting the stationary one? So part A says we're going to let go of this thing. What is the speed of this just before it hits? All right. How do we figure that out? That seems complicated. What do you guys think? Any guesses? Lots of ways to do it.
You could set the potential energy equal to the kinetic energy.
Thank you for being in class. Yes. So what we're going to do is, this is not part of chapter 6, but this is the easiest way to do it. Remember, energy is conserved. So we could figure out what the energy of the ball is in the beginning, and it should be the same at the end. Right? So when I hold the ball up here, so in other words, what we want is we want the kinetic energy of ball B plus the potential energy of ball B, right? The initial ones. And that should be equal to the kinetic energy final plus the potential energy final. Right? Of ball B, right? Ball B. Okay? I wrote that in the wrong spot. Kinetic energy of B, final, B, final. Okay? So what's the kinetic energy when I'm holding the ball up in the air? Well, let's write this out. Kinetic energy would be 1/2 mass times the velocity squared plus, what's potential energy? You guys know it off the top of your head? mgh, very good. So this will be mgh. This is the mass of the second one, so we're going to say m sub b. So it'd be m sub b gh right here, right? And then this one over here will be 1/2, and this is the initial condition and the initial condition. So those are all initial conditions, and this would be m b final. And this has a velocity, which is the final velocity, so we've got like I. Well, I'm getting a little sloppy here. Let me slow down and write all this stuff properly. This would be like the initials and this would be the initial. And then this would be the final. I could write it this way too. And then MB, well, I don't need to write the initial and final for the mass, right? Because that doesn't change. MB, G, and then H final, right?
Mr. Adam,
Yes.
couldn't you just have the 1/2 mv squared equal to the potential energy and then solve that for like velocity?
Yeah, but I want to remind you guys that where that comes from is from this.
Oh,
Okay. So this, the cool thing about this is what term is in every single term? Huh?
Mass.
The mass. So if I take everything and divide it by the mass of the ball, that drops out. In other words, this kind of cancels with everything here, right? All these masses cancel out, which will make it a little easier for us, right? What is the velocity of the ball in the initial phase there? What is that? What's the initial velocity of the ball? I lift the ball up just before I let go. What's the initial velocity? Yeah, 0. So this whole thing goes away to 0, right? So this is 0, right? Oh wait, let's not get too far ahead of ourselves. I guess what we're going to do is we're going to say 1/2 V, and we all know now that we have the initials on the left-hand side and the finals on the right-hand side. So this is the velocity squared. Did I write down the square? No, I sure didn't. This is squared. I forgot about it. Did I write it down? Yeah. All right. So this is the initial velocity plus GH initial is equal to 1/2 the final velocity squared plus GH final. Okay? And so the initial velocity is 0, so that goes away. Here I have GH, so I've got 9.8 meters per second squared, and I'm going to write that like this. Times the quantity h, which is 0.1 meters, right? And that's it, right? Now that should be equal to 1/2 times the final velocity, but I don't know what that is yet. Okay? Squared. Plus, now what is the final height when we let go of the ball? Yeah, well if this is 10, what's this? 0. So my final height h is 0, so what happens to this term? Goes away. So that's 0, right? So I've got 0 plus this. You guys with me so far? All right, I think we're doing okay. Mr. Adams is trying to hurry because, you know, sometimes these physics problems kind of drag on forever. But at the same time, I don't want to forget stuff. So, all right, here we go. So what is 9.8 times 0.1? Well, let's see. You guys get your calculators, I'll race you. Everybody pull your calculators out. There's nothing funny about that. Get your calculator out. I'm serious about mathematics.
This is physics.
I'm serious about...
Siri? What are you serious
I'm
about?
serious.
Totally serial.
I can't breathe, man. It's not... Oh, yeah. So this is 0.98. But what is it? 0.98 what?
Meters.
It's meters...
Wait, I thought this is 9.8.
9.8 meters per second squared. And then it's 1.8 meters. So it's like meters squared over second squared, right? Yeah, I forgot the 9.8. Oh man, we better slow down. Over second squared, because I want to make sure I get it right.
But what happened to
Isn't
what
it
goes on to 0.1? Yeah, why is it nothing to 0.1 meters?
where did
There we go.
There we go. Does that make you feel better?
Yeah.
Now, the reason Mr. Adams is pausing, and I'm trying to make sure that I don't forget something, but I just realized I think I'm okay. I'm pausing because I have this 1/2 here. So now this is equal to 1/2 the final velocity squared. Okay? So now what do I do algebraically speaking?
That's supposed to be a
It's going to
0.9.
be 0.98.
Yeah.
Yeah, I know. I'm trying to do 4 things at once. Thank you for. It's good to know you guys are paying attention. All right. So what do you guys think? What do we do next?
Get the velocity by itself.
And how do you propose we do that?
What?
Well, normally we would. Okay, so let me restate it. She said get the velocity by itself. So normally, what would we do with this number in front of velocity?
Times by 2 times by 2.
Yeah, we'd multiply by the reciprocal, right? So this would be multiplied by 2. So I'm gonna multiply that by 2 over 1, and whatever I do on one side, I gotta do on the other side. So that cancels this. And what do we got? 1.96 meters squared, seconds squared, equals the final velocity squared. Are you guys with me so far? So I love that I got an equation, but really I don't need velocity squared, I need velocity. So what do you propose? So when I take the square root of this side, right, I've got to take the square root of everything on this side. But one of the properties of radicals is that I could do it like this. And I'm writing it this way on purpose. I could do this, this, and this. That's the same as the square root of 1.96 meters squared all over seconds squared. It's the same thing. It really is. Trust me. I would not lie. Or at least not about math. Tired, man. All right. So then this becomes just velocity. Now what's the square root of 1.96? I'm going to double check because I've been burned on students giving me the wrong answer before. But she says, I'm just kidding. No, I'm not. It is 1.4. So just...
It's what?
It's 1.4.
what?
It's also in the back of the book.
What?
Don't get so
what correct?
this time. No, I'm very proud of you. I'm very happy that you got the right answer. That means you had a great math teacher.
Okay.
Miss Shem was so good
Mrs.
at us.
You guys are name all the other math teachers. All right. So anyways, just out of curiosity though, what we want to do is I want to show you guys this. I know you know how to do it, but I'm going to plug it in anyways just to check. And it is 1.4. Okay. So then it's 1.4 what though? Oh, she didn't say that, did she? Well,
Neither
did you. Alyssa said it.
Ooh.
I asked the question because I knew the answer. Does somebody want to battle me in math?
Roasted.
Bring some friends on a lunch.
Bring some friends in a lunch. It's going to be a long day. No. All right. So now that's the answer. We're done, right?
Yeah.
No.
Let's see.
Yeah.
Woo! Woo! Woo!
Well, hold on.
That's only part A, silly. Oh my
Yeah.
God.
Stop. Don't get too excited. So it says, consider the 2-string suspended balls with the mass of 1.5 kilograms. And then it says, one ball is pulled back on the line so the other is a vertical height of 10 centimeters, then it's released. What is the speed of the ball just before hitting? So this is the speed of the ball just before hitting. Now I suppose at some point in time we might want to consider, is that a negative velocity or a positive velocity? We'll talk about that in a second. But yeah, that's only part A. We're not quite done yet. Part B says, if the collision is completely elastic, what height do the balls swing? So what they're saying is, if this is the case, when the balls collide, so let's think of this. So what they're saying is that this is Newton's cradle, and when these two collide, the instant they collide, this one has a velocity of 1.4 meters per second. Now it's an inelastic collision. Now in Newton's cradle, normally when you do this, when the one ball hits, the other ball goes. And then that's the cool thing about it. And they just kind of do this, right? Is that funny watching me do that?
Yes.
It reminds me of that
Yeah.
thing. I can't do it. I can't do
But it's an inelastic collision, which means what? That kinetic energy is not conserved, but what is? Momentum. And they want to figure out what the height of the two balls are. So we've got to figure that out. So now, the one way that we could do this, it says when they stick together, their speed just after the collision, okay? Their speed just after the collision by momentum conservation would be what? Let's calculate that. So now we've got to do conservation of momentum. So our initial momentum, and I'm going to write it the way your textbook does. When I took my physics coursework, I always used PI, which means initial. I always use the subset I and the subset F, which means final. Your textbook uses this to mean initial, and they don't use anything at all for final. So if Mr. Adams accidentally writes P sub I, I'm talking about all the initial conditions. If I accidentally write F, I'm talking about the final conditions. So what we're talking about here, we have some momentums of A and B. So this is A and this is B. Now the mass of A times the velocity of A in the initial plus the mass of B times the velocity of B in the initial should equal, and we'll do this in a different color, the mass of A times the final velocity of A plus the mass of B times the final velocity of B. Okay? Alright, so now let's do some math here. Now the only thing that's weird about this is what do we know about the velocities if they collide together? Yeah.
The velocity isn't it not as great as when?
Yeah, this second half, if it's an inelastic collision, this is a little different. It's technically mass A plus mass B times one velocity, right?
Yeah.
But if I leave it the other equation, I could think of it like this. I've got mass A, velocity A, plus mass B, velocity B, but remember that mass A, or velocity A is equal to the same velocity of B, right? Is that right? Yeah. So technically, I could do it like this. Which is the same thing I just wrote down, right? If I pull out the VA, I've got MA plus MB times, if I pull out the VA, right? That's where that comes from. Okay, so now we got to solve this, all right? Well, here's what we're trying to figure out. I think the question they're asking us is, what is this? Okay. So we'll slide that up there in place. And so initially we know the mass here and we know the velocity here, but what's the velocity of A initially? Yeah, the velocity of A initially at the beginning is 0, right? So this whole thing kind of goes away. So I've got 0 plus 1 point, is it 0.15 kilograms? And then we said times the, what was the velocity? 1.4 meters per second. And that should equal, now here I'm going to have, here I'm going to have, I should have kept that the same color. Here I'm going to have 0.5 plus 0.5 and that's going to be in kilograms, times the quantity, and I don't know what this is yet. All right. So let's multiply this out. I've got 1.4 times 0.15, and that's 0.21. Why don't you guys do that too on your calculators, just to make sure we're getting the right answers. Okay. Yeah, it's 0.21. Okay. But I'm going to write it in because I feel pretty confident. So I'm going to say 0.21 kilogram meters per second. And now we're calculating conservation of momentum. We're going to do a little bit of a dimensional analysis thing here. In the dimensional analysis, what we find is that the unit should be kilogram meters per second. And that's what we have. Good. So now, this is really 0.3 kilograms times our velocity. And really, it's not velocity A, it's like velocity AB, right? It's like the velocity of both of them. What do we do next? Divide by 0.3 kilograms on both sides. So now I'm going to divide that by 0.3, and I get 0.7. Now, I knew the answer when we started. Remember the astronaut? Remember that video we watched with the two tennis balls? What did he say the velocity of the two tennis balls would be if they collided and stuck together? Exactly what? Exactly 1/2. Guess what this is? 0.7 meters per, because the kilograms cancel. 0.7 meters per second is the velocity of the two, which is exactly 1/2 of what the velocity of A was, right? Isn't that exactly 1/2 of that? Now you probably said, why didn't you just write that down?
Yeah, why did
Well, because it works out that way, but what if it's not exactly 1/2? What if they had different size masses?
Well, then the problem lied to us.
No, this is how you get the answer. This is how you get the answer. You go through that work. Now, does that tell us the height? Because that's what we were supposed to find, was the height.
No, we're not.
No.
Oh my god.
So now, wait a minute. How do I find the height?
Give us a question.
All right, so we've got. Here's what happens. This is the ball. We lift it up. It collides. Then they both hit. All right. When this hits, it hits with a velocity of 1.4. But it's an inelastic collision. So then both of them stick together. But now they're moving with a total velocity of 0.7 meters per second. And what we're asked to find is how high do they go? If this is where they started, how high do they go to get here? How do you find that? Well, how did we figure this out? This was a height, right? How did we figure that out? Conservation of energy. So if I want to do the conservation of energy of this picture here, how do I do that? Well, it's one mass because they stay together. So at this point, if we only consider this, you could treat the two like they're one with a mass of what? This has a mass of 0.3 kilograms, right? Because this one is 0.15 kilograms, and this one is also 0.15 kilograms. Okay? But those two are going to be staying together. What is their velocity? Well, their combined velocity is 0.7 meters per second. Hey, what can I do with that information? Well, I can find the initial kinetic energy. So what we're talking about it's almost like the roller coaster stuff that we did. I'm going to have a kinetic energy here. But when it swings this way, just before it stops, what happens to the kinetic energy? It becomes 0. And then what does it contain? Potential energy. Now, technically, we could go this route and write all this stuff down. I'm going to show you a little bit of a shortcut, though. Okay? So now the shortcut here would be my initial kinetic energy plus my initial potential energy, and then I'm going to have my final kinetic energy plus my potential energy. Did I say potential kinetic energy last time? I think I did. So this is my initial, and this is my final. Now we could save ourselves a lot of work if we talk about it. At the initial phase right here, so this is the initial phase, right here, what is the potential energy? How high up has that moved? Well, I can arbitrarily make this 0, and then I can make this, if I have these two here, I can make this h, right? So remember that potential energy is calculated by mgh. What's h here at the bottom? 0. So the potential energy in the beginning is 0. Right? Now, let's go to the final part of it. When the ball reaches right here, as high as it's going to get, what is its velocity? Just before it falls back down, it's going to rise up, stop. What's the velocity? 0. So what's my kinetic energy, the final kinetic energy? 0. So what I have is I have the initial kinetic energy is equal to my final potential energy, and the height is listed in that equation. So my initial kinetic energy is going to be 1/2 times the mass, which is 0.3 kilograms, times the velocity, which is 0.7 meters per second, and we set that equal to the potential energy, right? Because this is, and this is squared. So it's 1/2 the mass times the velocity squared, right? That's kinetic energy. And so let me write that down. Kinetic energy here. And then we're going to find the potential energy, which is just going to be the mass, which is 0.3 kilograms, times g, which is 9.8 meters per second squared, and then times h, which we don't know yet. You guys with me so far? Does that make sense? It's almost time to go. Hang in there. We're almost done. So now on my calculator, I'm going to say 0.5 times 3 times 0.7 squared. And let's see, is that what you guys got?
Yeah.
Yep. I think that's right. So now it's 0.735. Now our unit is kilogram. But now when we square the meters, isn't it meters squared over second squared? Because you gotta square that too. The units, right? Did I square that though?
Wait, why is it, when you multiply them together, isn't this supposed to be 0.3 or 0.5?
Oh, it's supposed to be 0.3. Okay, you're right.
0.0735.
So let's do that again, okay? That's why I asked you guys. Times 0.3 times 0.7 squared. Should be the same number, but we got to move it over, right? So technically, this is 0.7, right? Good catch. You caught that. Good job.
Thank you.
So now we just got to multiply this one, which is 0.3 times 9.8. So we say 0.3 times 9.8, and that's 2.94, right? All right, I hope this works out. 2.94, and then the units is going to be kilogram meters second squared times h. So now I'm going to divide by 2.94 kilogram meters per second squared. Now when I get over here, I'm going to divide by, and this is one way I like to do this. This is how I check my units. I'm going to divide by 2.94. But now with the units, when you divide by a fraction, what do you really do? Multiply by the reciprocal. So I'm going to take my units and I'm going to reciprocate it, and I'm going to have an s squared here all over a kilogram meter here. Does that make sense? So now what happens with our units is the s squared and the s squared, which is the time, second squared, those cancel. My kilograms cancel with my kilograms. And one of these meters cancels with one of these. So I'm left with 1 meter on the top, right? Okay. What was the numbers? It was, what was it? So it's that divided by that. Okay. So I've got 0.0735 divided by 2.94. So I got 0.025. Now that's the answer in meters, and guess what? That's the right answer because I got 0.025 meters, and that's the height. Now they originally gave us the answer in centimeters, and I just checked my notes that I noticed in the back of the book. It gave the answer in centimeters. So, how do I convert this to centimeters? Well, 100 centimeters is equal to 1 meter. So if I multiply those through together, the meters will cancel with the meters, and I multiply by 100, which is like moving the decimal 2 spots, so it'd be like 2.5 centimeters. And that's the answer you get in the back of the book. Any questions?